Okay, so welcome to the second talk today in the hottest conference of 2020. Today's speaker, or the second speaker, is David Jas Myers from Johns Hopkins University. His title is Higher Schreier Theory. Based on that, I'm hoping that every line of this talk rhymes. Go ahead, David.
Thanks, Dan, and thank you, Dan and Chris, for inviting me to give this talk and for organizing the hottest conference on the block, and to all the organizers. So before I get started, I want to take a little moment in my platform to advocate for defunding and demilitarizing the police. So gains are being made right now, and I encourage all of you to make a fuss locally about it. So today, I'm going to talk to you about higher Schreier theory, which is a story all about group extensions. And so before I get into that, I want to recall what a group extension is and a little bit about why we would care about them. So let's see. There we go. Okay. So a group extension is a way of saying when one group is built out of two other groups in two different ways. So the definition here is that we have a group G extended by a group K, and I'll point out here, and for the last time, that sometimes this convention goes the other way. So some people call this an extension of K by G, which is terrible. But G by K is the way I'm going to be going here. And it's a short exact sequence that has K as the kernel and G as the co-kernel. And so E, we often meronymically refer to as the extension here, but really the extension is the data of this short exact sequence. And so a short exact sequence is an exact sequence. So for two maps to be exact means that the image of one is the kernel of the other. And so a sequence is exact when all composable maps in it are exact. And so here, what that really ends up meaning is that I is injective, P is surjective, and the kernel of P is the image of I. And for the rest of the talk, I'm just going to identify the kernel of P with K itself. So, and we'll call K the kernel of this extension. So as you can see here, one of these ideas of what's happening here is that if we have this quotient P, this quotient map, then the inverse images under any element of G is a coset in this quotient, and the cosets are all bijective, merely bijective somehow, with the kernel. And so you can see E is being built up out of the multiplication of G, acting on, in some weird way, the group K, so that they form together a new group E. And so a trivial example of this is the one I have below, which is forming pairs. So here, it's an extension of Z10 by Z10. And on the left, we include Z10 on the left component. And then the second map, we project off the right component of our pair. And as you can see, the kernel here is going to be precisely those things for which J is 0. So that's exactly the image of the other one. And so this is an example of a trivial extension. And here's a less trivial but very similar one. So we can write a number between 0 and 100 with a pair of digits, right? That's how we normally write it. We write it, say, ij, where I and j are numbers between 0 and 10. So it looks superficially like the top example. However, there is an extra little bit. The multiplication of a number between 0 and 100, considered as a pair of digits, is not, or I should say addition, really, is not just adding the digits together, right? We have to carry. And so in here, what you can see is we include Z10 into Z100 by multiplying by 10. So that's including it in the tens digit place. So it looks a lot like the first pairing. And then the second one, we mod out by 10. So that's like picking the second element of the pair. And in general, all extensions are really group structures on the pair. But the way that multiplication in G here, in the right group, acts on the multiplication in K in the kernel is twisted, right? Because we have this carrying operation. So that's what's interesting about group extensions. There are many group extensions between two groups. And so if you know the famous super theorem of the classification of finite simple groups, part of the reason that it's sort of this is sort of the mythological story told about that theorem is that the reason we're interested in classifying simple groups is that all finite groups are built up by extending simple groups. And so that I'm not going to talk about that whatsoever. I just want to give you a sense of like why we might be interested in finding out what extensions are possible between groups. So here are two special kinds of extensions we'll be looking at a lot. So an extension is split if the quotient map P has a group theoretic section. So if you're a believer in the axiom of choice, then P is always surjective. So it might always have a set, or it might always have a set theoretic section. And even if you don't believe in choice, it might sometimes have a set theoretic section. But for the extension to be split, it means that S is a group theoretic section. And another example, and this only really works if K is abelian, although at the very end I'll maybe talk about how we can problematize that idea. But an extension is central if the kernel lands in the center of E, and the center is all elements of the group that commute with every other element. Okay. Okay, so this talk is all about classifying group extensions. So here's the first kind of classification theorem you might see. And this is often presented not as a classification result, but I would like to interpret it as a classification result. So split extensions of G by K are classified by group homomorphisms from G to the automorphism group of K as a group. So this is actions, homomorphic actions of G on K. And it's done so by forming the semi-direct product. So the semi-direct product specifically tells you how to twist the action of the kernel, the multiplication of the kernel, by the multiplication of G here. But because the multiplication of G is left untouched, these are sort of split. And so, yeah, so this is often not presented as a classification result. At least I didn't learn it that way, but I just learned it as how you construct the semi-direct product. And oh, look, semi-direct products are equivalent to split extensions. But it's sort of one of a large number of classification results. The second of which is very famous, is that isomorphism classes of central extensions of a group G by an abelian group K are classified by the second group cohomology of G valued in K. And so this leads to a natural question, which is, can we classify all extensions? And the answer to that question is yes. We can, and in fact, it has been done. Nearly 100 years ago, Otto Schreier did this. He classified all extensions, and he did it by giving explicit cocycle conditions. And so this has come to be known as Schreier theory. You might wonder, why is it called Schreier theory and not Schreier's theorem? The answer is because it has been pushed, extended, generalized. The context has been changed. It's been done for all sorts of different things. So now sort of Schreier theory refers generally to the science of studying extensions of objects, but in particular group extensions or group-like extensions. So we're going to talk about higher groups here. So to give you a little example of the classical theory of higher groups, what I'll call an axiomatic two-group, or which normally would be called a two-group, a categorical group, or a GR category, is a monoidal groupoid where every object has an inverse of the isomorphism. And so these are very common objects. In fact, so for example, this is an example that shows up in physics sometimes, although don't ask me how, I don't know, but I've heard. It's called the circle two group. And what it is the groupoid is one-dimensional normed complex vector spaces. And then the monoidal product is the tensor product. And what we'll note is that everything has an inverse because we can take the linear dual and evaluation here. Remember, these are one-dimensional. So we always have this evaluation map, but here the evaluation map's actually an isomorphism. And so we get this linear dual. We get this invertible multiplication by tensor product. So two groups are really interesting, but there's a sort of classical way to study them via a presentation, which is known as a cross module. And at this point, if you're starting to tune out, feel free to tune out for this in the next slide. We're not going to use any of those definitions, but I want to give you a sense of what the classical theory is. So a cross module is an action of a group on another group, right? And a equivariant homomorphism back, which satisfies the specific identity, like so. And again, you don't need to remember this. Now, the theory of two groups presented this way gets a little complicated. So here is the definition of a morphism. A morphism can be presented by something called a butterfly. And the reason this definition flows off the end of the slide is because we won't need it. My point of having it here is just to show you that when you're trying to work with two groups in the traditional sense, it can be quite complicated. Now, of course, these can be very useful calculational tools, but for theory, it's nice to have sort of a more synthetic way of working with these objects. There's I titled the slide two group formulations, but in fact, Eilenberg of MacLean here, they started by reformulating Schreier theory into the language of group cohomology. And I think, I'm not certain, but I think this was one of their motivations for articulating group cohomology in the first place. Dedeker extended this idea further. Grothendieck brought it to sheaves. Giraud understood it as a form of non-abelian cohomology, and Breen did a lot of things with it. In particular, Breen showed that the isomorphism classes of all extensions can be understood as this reduced second cohomology of G valued in a cross module. And that cross module is given by the homomorphism, or the K acting on itself by conjugation. And so if you know a bit about cross modules, you'll know that the cross module represents the two group of automorphisms of K. So this is the groupoid whose objects are automorphisms and where monoidal product is composition. And the morphisms are conjugating elements. And so what we can say is what we can say is that the extensions of G by K are classified by two group homomorphisms from G to the automorphism 2 group of K. And so the nice thing about this formulation is that the split extensions were classified by homomorphisms from G to the automorphism group of K. So this is sort of just, if you loosen it in this nice two group theoretic way, you get all extensions. And so this is what we're going to extend here. So in his paper, Higher Schreier theory, Breen extends this theory to stacks of two groups. And we're going to steal this title and extend it to stacks of all higher groups, but we're going to use homotopy type theory, which is going to make our work significantly easier than the Herculean effort that Breen has done to bring this to stacks of two groups. So our main theorem will be that for higher groups G and K, and I'll explain what higher groups are, an extension of G by K, the type of extensions of G by K is equivalent to the type of higher group homomorphisms from G to this automorphism higher group of K, which is really the automorphism of the type BK of K torsors. So this is the plan of the talk. We're going to recall what a higher group is. We're going to see a proof sketch of the main theorem. We're going to go through a few corollaries, and then we're going to talk about central extensions. And so the subtleties and directions part, I actually cut from the talk. I left it here just as an invitation that if anyone notices the seams at the end of the talk and is feeling uncomfortable with the final corollary presented, that this is an invitation for them to ask me about it. The epilogue to the story I'm going to tell is a little wild, so, and very interesting, but it's not going to be part of the main talk. All right. Are there any questions before I go on and get started?
I have a quick question.
Mm-hmm.
previously you said extensions. So Schreier helps you classify all extensions of groups. You're not qualifying that at all. You really do mean all extensions of groups.
I really do mean all extensions of G by a non-abelian K, yes. Yeah, that's what's cool about it. Yeah. Although yeah, please.
So in the theorem you mentioned a slide or two ago that all extensions are classified by these two group homomorphisms.
Yes.
Here, G and K are still just groups, right?
Yes, G and K are still just groups, and we're going to do it for high groups.
Right. So, but what is the two group? Like, how are you treating G as a two group here?
Oh, so a two group is a monoidal groupoid with a property. And so if G is a group, you can consider it as a discrete groupoid with a monoidal structure coming from its actual multiplication. So it's a discretely included two group.
I see. Thanks.
But just like you know, pseudo functors from a category into cat are different than strict functors. So two group homomorphisms are different than sort of strict one group homomorphisms into sort of the automorphism group. It's different to go two group homomorphisms. That extra data is doing a lot of work. Okay, great. That's fun. I can see the thumbs up. Any other questions? All right, I'm going to continue on. So homotopy type theory has a really interesting and novel and deep, like fundamental shift of perspective on what it means to be a group. So the shift of perspective is that a group is going to be the type of self-identifications of a given object of some type. And in fact, I put the word higher here in parentheses because this is a shift of perspective on what it means to be a group in the traditional sense. It's also going to be our definition for a higher group. So we'll come back and redefine what it means to be a regular group out of a higher group. So instead of axiomatizing the algebra of self-identifications, like saying you can compose self-identifications that's associative, you have a unit, you have inverses, blah, 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 we work with the type of all objects which are identifiable with our given fixed reference object. And so this is a really important definition here I'll use a lot. B ought in the type capital X of little x is the type of all things in capital X which are merely identifiable with our reference point little x. And so we consider this as a pointed type. We need to remember that reference point because we need to remember what we're self-identifying. And univalence is going to handle the interpretation of the identification types, so that equal sign there, identity types. Univalence is going to handle the interpretation of those as whatever kind of symmetries we're actually interested in. So if we have an axiomatic one group and let me say an example of this would be so suppose we want to study the symmetries of a square. So the dihedral group. So what we could do is we could define the set of symmetries of the square. So it's the set of, say, affine symmetries of the plane which fix this particular square. In homotopy type theory, instead of looking at that together with its operations of composition and identity and so on, what we would do is look at the type of squares. And we remember our fixed reference square, and everything we're going to do group theoretically, we can do with that type instead. So we call this the D-looping here, D, G. So if G is any axiomatic one group, by which I mean a group where we actually have the structure, we can take BG, it's D-looping here, to be, so we can understand any group, we can sort of solve this problem of finding it as the type of self-identifications by finding it as the self-identifications of itself considered as an action on itself, a left action. And so this is the type of torsors, actions which are identifiable with G acting on itself. So this theory and this perspective have been developed by a number of people in the homotopy type theory community. I think the first explicit saying of it was a blog by Mike Schulman on the Uncategory Cafe. Someone can correct me if this is wrong. And then Ulrich, Flores, and Egbert have a great paper called Higher Groups in Homotopy Type Theory, where they prove a nice theorem about it, which I won't say because I don't want to confuse the issue here. And they developed the theory a little bit there. So, and I also want to plug the Symmetry book, which is an in-development book by Unimath. I think it's mostly by the same people, but also other contributors as well. And that's going to be sort of a group that takes this perspective as a fundamental definition of what it means to be a group and develops undergraduate algebra from that perspective, which I think is really cool. So here's the formal definition. A higher group is going to be a type which is identified with the loop space of a pointed zero-connected type. So BG is called its delooping. And so G is going to be identified with the base point of BG and its self-identifications. Yeah. And so an n+1 group is a higher group of symmetries of an n-type object. That's the the heuristic way of understanding it. In particular, it means that its delooping is an n+1 type. So a one group is a group of symmetries of a set level object, and its delooping is a groupoid. Oh, thank you, Noah. So that's the link in the comments. All right. So a one group is what we call usually a group. And a two group, if you see here, a two group is the symmetries of a groupoid level object. Its delooping is a two groupoid. It itself is a groupoid, just like a group itself is a set. Okay. So a homomorphism of higher groups is just represented by a pointed map between the deloopings. And here you start to see the simplification coming in. So we don't have to check anything. We have to give an extra data, which is the pointing. So an example of how this works is the determinant. How do we represent the determinant in the homotopy type theory perspective? Well, we should understand what GLN is from the homotopy type theory perspective. Like by definition, I'm going to take our base field to be the real numbers. By definition, GLN is the linear symmetries of the affine n space of Rn with a base point. So in other words, we take the vector space Rn and we look at its symmetries. So we can take BGLN to be the type of n-dimensional vector spaces. So then we can see that the problem of constructing this homomorphism from GLN to GL1 is given by constructing a pointed map from the type of n-dimensional vector spaces to the type of one-dimensional vector spaces. So we can do this by taking the nth exterior power. So if you have an n-dimensional vector space, its nth exterior power is a one-dimensional vector space. And moreover, if we look at how this acts on a symmetry, it gives us the nth exterior power, the functorial extension of the nth exterior power, right? That sends it to an element of GL1, a number, and by the characterization of the determinant, by certain kind of anti-commutativity properties, that turns out to be the determinant. This is pretty cool. And another interesting example is what it means to be an action of a higher group on some type. So a higher group, and all higher groups, remember, are of the form of automorphisms of some object in some type. So an action of that on a type is going to be a homomorphism of this sort, right? That's just the normal definition of action. It's a homomorphism into the automorphism group. But let's look at explicitly what this means, right? So C here is a construction. It takes a Y, which is identifiable with X, right? And it gives a type C of Y. And then the only extra bit of data we need is a way of identifying C of X with the type we're acting on, A. So for example, the action of GLN on Rn, this sort of tautological action, it's given by taking the underlying type of a n-dimensional vector space. So it looks like the identity here, but it's really the underlying type function. And of course, we have to choose how to point this, and we can point it at reflexivity. So if you look at how transport in C acts, you can see that transport in C precisely is going to act by the action of GLN. Are there any questions here? Right. So an axiomatic one group is what we normally mean by a group. And so we could do things this way in homotopy type theory. But it turns out that taking this more general, higher group theoretic perspective actually can give us some insights about one groups, about the theory of one groups.
I have
this is
question.
Oh yes, please.
The group that you construct, that you call GLN, but it's not like a topological group, is it? Though it's still a one-dimensional group, right?
That's a very a good question. So it will depend on how we interpret our homotopy type theory. So remember, homotopy type theory has semantics in all infinity toposes, and if we interpret it in the infinity topos of homotopy types, then this will be as a sort of discrete group. However, if we interpret it as in the infinity topos of stacks on, say, Euclidean spaces and smooth maps between them or continuous maps between them, then we will get it as a Lie group or a continuous group, a topological group measured in that way. And so, in fact, depending on the interpretation you're in, you can get the topology coming for free. And I'll actually use that a little bit as one of my corollaries, so thank you. Are there any other questions? Okay, I'm going to keep going. So there's a big theorem, which is that the theory of one groups, which includes homomorphisms, actions, torsors, blah, 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 all expressed in the normal way, axiomatically, is the theory of one groups all expressed in the hot way is equivalent to the theory of one groups all expressed in the normal axiomatic way. And I'm citing the symmetry book here because I think it appears there. I would love if someone could point me to a reference. Maybe it is there. If someone could tell me about that, that'd be great. If not, then I'll have to call this a folklore theorem. So we expect this to work for higher groups. As far as I know, some of
David, is there a particular? I mean, it's developed all throughout these chapters 4 or 5 in the symmetry book. I mean, we're still working on these, but if there's a particular result you want to know about, like we can plug those. But start with those chapters.
Great, thank you. That's great. So yeah, So the whole result is there, like spread throughout sort of the idea of the book, which is starting from the homotopy type theoretic perspective, reconstructing the axiomatic perspective. So the analogous result for two groups, maybe Ulrich, you could tell me if this appears anywhere, or if people are working on it. But because we're going to end up with a homomorphism, a two-group homomorphism result, so even to study one groups using this higher Schreier theory, you'll need this axiomatic theory of two groups to get the cocycle conditions out. And we can't give, so the proof is long. Say like check out these 3 chapters of a book. And there's a lot of work in it. It's not specifically hard, but it's a rising C kind of theorem, right? We can't even prove, we can't even formulate an analog generally in homotopy type theory until we have a definition of axiomatic infinity group. So maybe Eric has something to say about this later in the week, of how to get these fully weak higher structures. I should mention that externally, we are talking about the theory of higher groups, thanks to the semantics of homotopy type theory. and a proof by Lurie that pointed connected objects in an infinity topos correspond to group-like infinity spaces there. Okay, so now I'll tell you about extensions of groups. So this is an example coming from physics, and one thing I want to emphasize here is sort of how these ideas, that the Hopf perspective actually is sort of a perspective that's quite native to physics and to mathematics if you just sort of take it at face value. So a Lorentz space, so these are all, I should have said it in the book here, but these are all definitions from a book on mathematical physics. And a Lorentz space is a vector space with this kind of norm. So it's identifiable with R3+1, that is 4 space, together with this norm here, the Minkowski norm. And the type of Lorentz spaces is therefore the type of old normed vector spaces which are identifiable with this space. So I've called that BL because the Lorentz group is, by definition, the symmetries of R4 preserving this norm. So Minkowski spacetime now, so a Lorentz space has a base point. Minkowski spacetime is not supposed to have an origin point. So what it is an affine space over Lorentz space. So every Lorentz space is in particular an abelian group. It's a vector space, so it's a particular abelian group, and we have this affine space, but the type of affine spaces over a Lorentz space V is in fact the delooping or a delooping of V as an abelian group. So I've written it here as BV. And so we can form the type of Minkowski spacetimes as a pair consisting of a Lorentz space and an affine space over it. And I've called it BP because its delooping turns out to be the Poincare group. And so by construction, immediately you can see that we have this fiber sequence here. And this fiber sequence is what I'm going to mean by an extension. And so one thing I want you to note here is that BV is a construction of a type that when you plug in R3+1 for V, gives you B R3+1. And so this is an important feature that we're actually going to use in to prove higher Schreier theory. And so we'll take this as our general definition of a higher group extension. It's going to be a fiber sequence like so. And you can show that if G and K are one groups, then this is equivalent to the usual definition of fiber sequence of exact sequence of groups or extension of groups. And a nice thing to note here is that BE, we want it to be zero connected because we want it to represent an infinity group, but we don't actually have to ask for that. In fact, just by being sandwiched in this fiber sequence, it comes for free. We just need it to be a pointed set fitting into this fiber sequence. So the fiber sequence we were looking at in the other page witnesses the Poincare group as an extension of the Lorentz group by the group of translations. And we can see also that this is split. So the BP, remember, is a pair consisting, it's a Minkowski spacetime, pair consisting of a Lorentz space and an affine space over it. So every Lorentz space is an affine space over itself. So we have a splitting. And that witnesses that this is in fact a semi-direct product, which is sort of this, if you know of this story, you might already know. All right.
When you say split, do you mean that there's a pointed section going from BG to BE?
Yes, exactly. There's a pointed section going back, and it's pointed as it's a section as a pointed map. And so that is the way of saying that sort of the section is group theoretic, is a homomorphism. Are there any questions about this? Okay, so I need a little definition here. So a lot of the actual work here is just a bunch of lemmas concerning these pointed families. So a pointed family is on a pointed type is a type family on the underlying type of that pointed type, together with a point in the fiber over the base point. And so the type of pointed sections, which I write with this dot arrow here, consists of a section together with a pointing. So it's just an equality of the base point. And the thing I want to note here is that a pointed family is not the same thing as a family of pointed types. Pointed and family don't commute. And the reason is a family of pointed types is a family of types with a section. Whereas a pointed family is, as this proposition on the bottom shows, is equivalent to a pointed type sitting over your pointed type via a pointed map. Okay. So now we can come to the main theorem, which is higher Schreier theory. So for higher groups G and K, the type of extensions of G by K is equivalent to the type of pointed maps from BG to B-OT-BK. So B-OT-BK is the type of all types which are identifiable with BK. So here's a proof sketch. So the way this proof would actually go is you do a bunch of shuffling using lemmas in this big dependent sum, and you don't actually, look at, you don't actually build the quasi-isomorphism back and forth. But if you extract from that what you get at the end, it will look like this. So if we have such an extension here, the pointed map BP corresponds to a pointed family over BG. But BG is zero connected. So all the fibers, and the fiber over the base point is equivalent to BK by assumption. So every fiber is identifiable with BK. And so it lands in B-OT-BK. In the other direction, we take the dependent sum of the type family. So if we have BG to B-OT-BK, remember B-OT-BK are types identifiable with BK. In particular, this is just a type family. So we can take its dependent sum, that's going to be DE. So that was easy. That's a lot easier than traditional Schreier theory. I would say that than Otto Schreier's Schreier theory, certainly than Breen's higher Schreier theory for stacks. And it's for all higher stacks of higher groups. Like, wow. Maybe I'll say quickly. One way I like to read this is extensions of G by K are given by actions of G on the type of K torsors. And I think this is sort of a nice, this is maybe a conceptual way of understanding it. So the question is, where did all the work go? Like, what happened? Where did all the work go? Where are all the cocycle conditions, right? And the answer is that all the cocycle conditions, they're hidden in the proof that the homotopy type theory approach is equivalent to the axiomatic approach, which, as I mentioned, is a long sort of rising C result. So all the work is back there. And the work is also in showing that B-OT-BK is actually can be presented by the groupoid I described earlier, so automorphisms with conjugations. I'll show why that's true in a little bit later, but there's a lot of work in extracting the cocycle conditions. However, I want to point out that we can actually use this result even without doing all that work. So I'm not going to talk about that work now. I'm just going to talk about how we can use this theorem. Okay. Are there any questions?
Maybe, David, maybe you could say a few words about how we went from short exact sequences to sequences that are short in the middle. You skipped that a bit, I think.
Oh,
maybe
yeah.
So for later.
No, not really. If I go down to here, so we have this fiber sequence. So what it comes down to is the connectivity. So if we take the loops of this, we're going to get this sequence of groups. And because BK is the fiber here, that means that if we take something in K and go forward to E and go forward to G, we're going to get into the identity. So we can just, from the fact that this pointed map is 0, the resulting pointed maps on groups are 0. So it's a complex. And then we need to show that it's exact. And the way we do that is by noting that since the fiber of BP, the rightmost map here, is BK, which is 0 connected, that map is 0 connected because BG is 0 connected. So that property extends to its fibers. And therefore, the looping of it is -1 connected, which means surjective. And similarly, we just run through and prove the characterization I gave at the beginning. So in fact, you do get this. So being a fiber sequence is stronger than being exact. Being a fiber sequence is stronger than being exact. It's more like being short exact. But there's ways to relieve that tension, I guess. So I won't talk about that now. Okay, I'm gonna keep going so I can do some corollaries. Okay, well, remember that the first result we saw, the first classification result, was that split extensions are classified by homomorphic actions of G on a group K, or maps from G to the automorphism group of K considered as a group. And we can directly lift this result up using higher Schreier theory. So remember that homomorphisms between higher groups are pointed maps between their d-loopings. So in particular, the automorphisms, the infinity group, higher group automorphisms of a higher group are pointed automorphisms of its d-looping. So we have this natural forgetful function, which is pointed by reflexivity from pointed types, which are identifiable with bk as a pointed type, and types which are identifiable with bk. By just forgetting the base point. And so we can, because of that, we have a really simple corollary, which is that split extensions of G by K are classified by homomorphisms from G into the automorphism higher group of K. And the way that works is noting that, remember, so that the result humming under this higher Schreier theory is that we're taking the equivalence between pointed families and pointed maps. And here what we have is pointed sections and liftings of that pointed family into a family of pointed types. So if we have if we actually have this action going through pointed types which are identifiable with bk, which are pointed, then every element of the fiber has a point, and we use that to construct our section. So here, coming back, I forget who someone's question was about getting topological groups. So if we work in cohesive homotopy type theory, so Mike Schulman's cohesive homotopy type theory, we can get a quick corollary here, and this is fun. If you don't know about this, just ignore it, but I'm just going to say it. So if we have a crisply discrete n group, and G is a crisp higher group, so an example might be a Lie group or a Lie groupoid, then the extensions of G by K are determined by the homotopy n type of G. So we have this identification. To extend G by K, it suffices to extend the homotopy n type of G by K. So in particular, if K is a 1 group, so just a regular group, and G is cohesively simply connected, so if it was a Lie group, it's a simply connected Lie group, then there's a unique extension, which is the trivial one. So this is a classical little theorem. It could be given as a homework exercise, you know, when someone learns about covering spaces, but here's a nice application. Okay. And another simple application, which we just spit out, is classifying extensions of the integers. So really easy. For any higher group, extensions of the integers is just the automorphism 2 group or automorphism higher group of K, in other words, aut BK. And the reason is because BZ is the free higher group. So extensions of Z, K is higher group homomorphisms from C to aut BK, BZ from Z to aut BK, but that's just aut BK. And now, in particular, we get this sort of nice result, which is that if we take B aut BK and we take its one truncation, we get the outer automorphisms of K. So if you remember that aut BK was like the automorphisms of K, but then the morphisms in it, the identifications between those automorphisms are the conjugating elements. Then if we truncate that, if we quotient by conjugating elements, we get outer automorphisms. And so taking this as either it's a definition or a theorem, take your pick, we have that the isomorphism classes of extensions of Z by K are just equivalent to outer automorphisms of K, which is a result about classical groups that I never do. It's kind of cute. Okay, so we can use this definition of outer automorphisms of K, or this theorem about what if outer automorphisms of K, take your pick, to get some nice, get a nice result about central extensions. So here we go back to Eilenberg and MacLean's interpretation of Schreier theory through group cohomology. So Eilenberg and MacLean call the abstract kernel of an extension to be the homomorphism from G to the outer automorphism of group of K, which is defined in this way. So defined by conjugation. You can check that this is well defined. And so if K is abelian, then it's true that an extension is central if and only if its abstract kernel is trivial. So that's just a sort of trivial little exercise in group theory. I hope it's believable looking at the definition, right? If that's trivial, meaning that that's the identity, then it's central. If K is abelian. And so we can define the abstract kernel very easily of a higher group extension, right? So if we have a higher group extension by higher Schreier theory, it's classified by this homomorphism from G to ought bk. But we also have this other homomorphism, namely the one truncation, which goes from ought bk to out k. And so we just take the composite, and that's our abstract kernel. And so using that, we can talk about central extensions. So to do that, I'm going to talk about what a center of a higher group is. So this is a definition I learned from Ulrich. So we have a higher group, and it acts on itself by conjugation. So remember, an action is given by a map from BK to a construction that takes an element of BK and gives you a type. And so here, if we take an element of BK and give the type of self-identifications, we can see that transport in this is going to act by conjugation, right? And so the center is the type of fixed points of that action, right? So this is sort of a mojo of higher group theory, is sections of this family are the fixed points of the action. And so here, ZK is the fixed points here, but we can see that by function extensionality, that's the self-identifications of a certain object, namely the identity. And so that notification there, that identification, allows us to deloop this. So we can see that ZK is actually a higher group. And what is it? It's, well, we can take the delooping to be all things which are, all automorphisms of BK, which are identifiable with the identity. And now what's really cool is that, so the center is supposed to be abelian, right? I mean, the center is things that are the fixed points of conjugation. They should commute with everything. And the way we have abelianness in higher groups is by further delooping using the Ekman-Hilton argument. So the Ekman-Hilton argument says that if something's a double loop space, then there is a reason that there's actually two Ekman-Hilton arguments, I think. There's a way that you can commute anything past another thing. And so we could prove that this was abelian in this sense, or we could construct a new delooping, and that's even better. So here's the delooping here. So you can see that B ought BK of the identity is almost like the automorphisms of something, right? But it's a little stricter. So we can see here is that we have B2ZK is types with a element of the set of an equivalence class, element of the set of identifications of A with BK. And if you deloop this, what you see is you get automorphisms of BK, and then the zero truncation there, it gets shunted down, it becomes a -1 truncation, and that's your merely identifiable with the identity. So we point this at BK and reflexivity at the identity. Okay, now B2ZK looks a lot like B ought BK, right? So B ought BK was types which are identifiable with BK. B2ZK is types with a element of the set of identifications with BK. So there's a forgetful functor. And moreover, the only addition is this extra element of the set of identifications, right? And we can get that as an identification in the one truncation. So sort of just by definition, we end up with this fiber sequence. And this is a really cool fiber sequence here. So I'll say about this is this fiber sequence justifies calling ought BK the automorphism 2 group of K, if K is a group. The reason is, if we remember, I said that it was its objects were automorphisms, its morphisms are conjugations. So if we truncate that, we're quotienting out by conjugation. By conjugation, we get the outer automorphisms. And if we look at what is sitting over the identity there, it's conjugations of the identity. That's the center, right? Elements that conjugate the identity to itself. So that's the center. And so you can see that this sort of justifies that result, and it would appear in a theorem. If I'm not claiming a theorem, but that's the idea. Okay, so because of this, we have that B out BK can be expressed as a dependent sum over B. So B out BK can be expressed as a dependent sum over B out K. And so recall that the abstract kernel is given by pushing forward the map into B out BK. And so as you can see that because it's a dependent sum, maps into B out BK correspond into maps into B out BK together with sections in the fiber. And that fiber is identifiable with B2ZK. So it's something like second cohomology valued in the center. So if you know the classical cohomological story, you know we're getting there. However, we have a really nice fact that we can say, which is that if the abstract kernel vanishes, right, then we just need to map directly into the fiber, right? And so that is, we get this result, which is that extensions whose abstract kernel is trivial, and I'll mention that that is in fact a proposition for any higher group, which is based on a very slight tweak of a result by Ulrich, Flores, and Egbert in their paper. We get that this is equivalent to maps from BG to B2ZK, which is sort of by definition, the set truncation of this by definition is H2GZK. So for one groups, we get that if K is abelian, we get that central extensions of G by K are in fact given by the second cohomology group. And that's it. So thank you all very much.
Great, thank you very much. That was a very nice talk. Let's thank the speaker. Okay, are there any questions?
I have a question.
Mm-hmm.
It's just, I may have missed something, by the way, so maybe that's the issue. So you in the very last thing, you talked about central extensions. So or for ordinary one groups, a central extension, the subgroup is has to be abelian. But that's not really what's happening in your higher framework. So I'm confused by the terminology central extension.
Thank you. So this is when I mentioned, I was wondering if you can see the seams in the final talk. This is exactly what I'm talking about. And the answer is it's very complicated. And I don't have a good story on it. So I can talk about it a little bit, but what I'll say here is the notion of, if you take the definition of central for an extension to be that the abstract kernel vanishes, then you don't need the kernel to be abelian. And such extensions by K, whose abstract kernel vanishes, are equivalent to central extensions by the center of K. And I can prove that in homotopy type theory. And I can look at it in the classical way. You just sort of, well, it's not super simple, but you get this, whatever. Okay, you just sort of restrict as naively as you can. You restrict to the center, and it turns out that this actually gives you equivalence on isomorphism classes. Another thing that's interesting here, and that you're picking up on, is that the way that this is classified is not in fact the same way that the normal theory is classified. And this is exactly what's happening here. And this is why I didn't give a definition of central for higher group. I only give a definition of central for regular groups where K is abelian. And so if you look at how this is actually classified, what you see is we take BG to B2ZK, our cocycle. We push it forward to B off BK. And what does that do? That's just taking the set. And then we take the dependent sum. Okay, that's an extension by K, not by ZK, but okay, that's fine. But the thing is, the extension by ZK you would get would be by taking the fiber of this map. And those are different things. So this is a different extension. As it turns out, those turned out to be equivalent and they turn out to be equivalent if K is abelian as a one group. If K is braided as a two group, so in general, there are three different things you might call central, and they're all, as far as I can tell, totally different for higher groups. And there's probably more, I mean. So you have the extensions of K, which are with vanishing abstract kernel, which are classified by B2 ZK. You have also the extensions of by ZK, whose abstract kernel vanishes, which are classified by B2 Z2K, where Z2 is the center of the center. And then you also would have things classified by B2K if K was already braided. And these are all different in general. So the answer is it's extremely complicated, and I don't have a good story. But thank you for asking this question.
Okay, thanks. If I can make a suggestion, you should probably come up with new names for these, especially since it's not even really central extension in the one group case, because otherwise it instantly becomes confusing.
So I will say that it is, when I say this theorem follows as a corollary, I do, for the one group case, I do mean the traditional theorem for the one group case where we assume K is abelian.
Certainly.
But
there is a generalization for the one groups, as you've said, that it also applies to. So
yes, and there's a lot of naming to be done.
Which I have always known, but I've never seen.
Oh, do you?
Talk about.
So I've never heard of it, and if you have a reference, I would absolutely love to have
I've never seen a reference. You just apply it to extensions where the centralizer of K inside E surjects onto G, and that's the ones that are classified. If you write that.
Oh, cool.
Yeah.
Oh, thank you.
I don't know. I've always looked for that, and I never see anybody give that a name.
Well, that's great. So, well, maybe you'd like to come up with a name for it.
I'd come up with something dumb, so don't ask me.
I have a question.
Yeah.
So in the classical Schreier theory, the sort of unhigher picture, the lower picture, is that there are two things. There's an action and there's a second cohomology class, right? And we sort of think of, there are extremes, like semi-direct products are where the cohomology vanishes, right? And central extensions are where the action vanishes.
Mm-hmm.
And, you know, as you work through it, this feels kind of natural, but what I'm wondering is, does the viewpoint that you get from this higher theory, do those things sort of pop out? Like, are these actually in some sense extreme rather than just, you know, like you had something about like, oh, it's a central extension if it factors through this thing. But like, is there some natural thing in the higher viewpoint where these two extremes just like pop out as actually extremes rather than certain conditions that one might hope for?
So the trick here is that I would say that they're not exactly extremes for the simple reason that that the action you get is not really an action without the cohomology class, right? Because what you have is, and map into you have an action by outer automorphisms, which aren't really automorphisms, and then the cohomology class is the cocycle tells you how to lift that outer automorphism action through specific choices of conjugation to an actual action. So because of that, it's hard to like specifically dial. I think, like, it's, for example, like you can't just like look at this fiber sequence and say like, oh, all maps here 0 out, you get an action. All maps there 0 out, you get a thing. But very close. So I think this fiber sequence sort of expresses it best, the best way I could possibly formulate it, which is that you have this fiber sequence here, and you can see that that represents the opposition between the action part, so maps into the outer automorphisms, and the cohomological part, which is maps into the fiber. And of course, the fact that that it's only the fiber over the base point which is represented means that one is, you know, twisted by the other. And in fact, if you know the regular story, you also know that there's an obstruction to there even being a lift, which lands in H3. And I can't thrice de-loop my center. So I really don't know where that comes in. I have an idea, but it's not following through. So the story at the end here is sort of like phrase a lot. So I don't really know exactly how I'd answer that, but.
Other questions? Mike, I can't hear you.
Hello?
There?
No.
No, that
I'm
was Ali, but Mike's trying to talk, I think, right?
No, this is me talking.
Mike was saying something.
Yeah.
Oh, is he? Oh,
Is that better?
Oh, there we go. Now
Yep,
we can hear you.
that's
Okay.
better.
Yeah, for some reason my volume tends to die unexpectedly. This is more of a comment than a question, I guess. You briefly mentioned a blog post of mine when you were talking about the history, and that was kind of news to me. Maybe there was a blog post, but it was just expressing folklore at the time. I don't really know very much about the history, but I don't remember inventing anything.
Thank you.
Okay.
I don't really know the history very well. Sorry. Yeah. So the ideas appear to have emerged from the mists of time, although it was only about 10 years ago. So.
Okay, I think Ali had a question.
I've forgotten my question, so it probably wasn't a very good one.
Sorry, Ali.
Okay. I have a question. These are extensions like that would normally be called as living in X1. Have you thought about higher X's, longer extensions?
So X1 is usually in the abelian setting.
Yeah, exactly. So you probably want
or like higher non-abelian extensions or something.
Well,
like this.
even higher abelian extensions. I'd be wondering if you thought about that.
I'll say that I've had thoughts about it, but I have no idea. So one thing that's tantalizing to me is that Ulrich and Egbert, I believe those two, yes, have this paper on n-exact sequences of higher groups, and I have a sneaking suspicion that these have a relationship to longer exact sequences, although maybe they can give a better sense if that hunch has anything to do with that's it. A hunch is maybe even a grandiose way of framing it, but yeah. Hopefully that's the next step. So.
Okay, we have time for one more question or comment.
Okay, so since you asked during the talk about the situation with two groups, so the axiomatic cross-module story or monoidal group words and so on. So I'm working with a master student, Johannes Schipp van Branitz, and he's formalizing a lot of these connections. So hopefully by the end of the summer, that should all be available in Cubicle Acta.
Oh, awesome. That's wonderful. That's wonderful.
I remembered my question now. I was asking if you had any formalizations, but I'm guessing you don't at the moment.
No, I don't. Although I should say that I don't expect this to be more difficult than any normal formalization. It's a lot of the actual proof is a lot of just shuffling around big blocks of dependent sums.
Okay, great. Well, let's thank David again. All right, and so that's it for today. Our next talk is tomorrow morning at 10:30 Eastern, and I hope to see you all there.